Hello boys and girls. So I wanted to make a video on Q deformations, Q deformed numbers. More on that in the description. But when I was writing down a kind of script, I figured I should start with a little bit more basic concepts and a more basic task. So what I want to do in this short video is motivate a question. And I would say the question right away for those who are advanced enough. And it's also a very basic question from a university level perspective. But the question I want to ask, and which will be related to some interesting algebra, is what is the limit as x, a real number, approaches a real number, for this expression, in particular when an integer n is bigger than another integer n. So what is the limit of a to x of that expression, and how to compute it, and what does it tell us? Like, what can we say about that? And of course, if you have some nice analysis techniques under your belt, then there are some moves where you can do that in a minute, less. But there are also some more algebraic approaches, and that's where I'm heading more or less with these kind of questions. And the most interesting case here that we want to look at is actually when m is just 1. So the question is really, if you take a number a to some integer exponent n, and the same for this variable, so this is a monomial, and this is some polynomial expression here in denominator, and then divided by a minus x, which naively is not defined for x equals a, but if you take the limit exists, and what is the value? Like, what is the value and why is the value it is, and what can we say about the result? Okay, so that is the question, and now I will take a step back and motivate that a little bit more. If we start looking at a function defined by 4 over 3 minus x in that case, and if you plug in some other numbers instead of 4 and 3, that will give a similar kind of graph. What you have is that you can evaluate this function f for some numbers. For example, if you plug in x equals 0, then you get 4 over 3, which is a little bit over 1. So x-axis, x equals 0, the value is 1 point something. If you plug in 1, then you get 4 over 3 minus 1, so 4 over 2, so that's 2. You see that it grows, and the distinguishing feature of that graph is that you are not allowed to plug in a value x, because then you end up with division by 0, right? If you were to plug in that case x equals 3, then you would have 4 over 3 minus 3, and that's not defined. And you can see that in the graph, in that there is no value. You cannot make an x here where you can nicely draw the graph. What happens on the other side is that if you look at an expression like that, then this is also not defined really for the value x equals 3. So it's the graph of this picture. For x equals 3, you don't get a value, but really for any other value x that you would plug in, if I plug in 2, then I get 3 minus 2 divided by 3 minus 2, that's 1 over 1, and the value is 1. If you plug in 1, then you have 2 over 2, the value is 1. So this is really the constant function. If you take this expression and take it as the body of a function, the definition of a function, then this is the constant function, except there is one value which is formally not the value of this function. However, you can still speak about the value in the sense that if you follow the graph along the line, if you compute the limit, if you go closer and closer and see where this ends up, so then there is indeed some value that you can take to be the completion of this graph, right? So you say the limit of x to 3 of this expression is 1, you know, it's at 1, even though the expression itself is not defined for just plugging in x equals 3. And for the next thing that I want to look at, I have here this simple algebraic manipulation that shows that if you have an expression a squared minus b squared, where a and b are some real numbers, then this actually factors into this kind of product. And so what happens if you have an expression like that is that you can use this formula for a equals 3 and b being x here, and plug this in, and then the 3 minus x would be here, and you can cancel it out, and what you get is then this expression. So except for the value where this expression is not defined, which is x equals 3, the value of this expression, if you plug in any number, will be that number. And you can easily draw the graph of that. This is basically similar to that, except, you know, a little bit mirrored. And here you also get this nice folding function, and an asymptote. In that case, this function would not be defined by x equals minus 3. Lastly, if we do not consider this expression where the square is in the denominator but in the nominator here, then you can play the same game and you get actually a linear function. So this expression, although it looks a little bit more complicated than a linear function, is really just a linear function, except for this one point where it's not defined. But evidently the limit of x to 3 of this expression would be 6 here, because if you plug in this simpler formula 3, you see this is the kind of the completion of the graph, right? And so this leads us to this expression, and for simplicity, let's say m equals 1, right? So that could be, let's say, 7 to the power of 10 minus x to the power of 10 divided by 7 minus x. And the nice feature of that is that this is also has a graph which actually doesn't have an asymptote. So this actually reduces to something very, very simple, or rather simple, like this. And the question is, why does that happen? Can you kind of give some soul to this expression to say why it doesn't break like this here for some value? And I don't want you to use, you know, analysis tools for that and do differentiation and so on. I mean, there are some tricks where you can get to the result simple, but I just want to do some cheap algebra, and it's actually related to that. So we want a generalization of this formula. We can apply it here, and then we get actually some character to the value of the limit here. Okay, thanks.